let's find what powers the sun. Let's take a look at what we call a hydrogen atom. It's comprised of one proton, and it has an electron going around it. And we call this by the symbol H. And as soon as we write the symbol H, we imply by using it that there is one proton in this atom. Now, if we add a neutron to this proton, then we have not changed the number of protons, so the element is still hydrogen, because an element is identified by the number of protons that it has. But it now has two particles in the nucleus, so we call that H2, or sometimes heavy hydrogen, or deuterium. So the H indicates the number of protons that are in the atom, and the 2 indicates the number of protons plus neutrons that are in the nucleus. So as you continue to add neutrons without changing the number of protons, you do not change the element, but you create what are known as different isotopes of the element. So let's examine the element helium, and as soon as we write Hg, we're indicating that we're talking about an element that has 2 protons in it. Now, the basic atom of helium also has 2 neutrons in it. So in its basic form, helium occurs in the helium-4 state, meaning it has 2 protons, which identifies it as a helium atom, and it also has 2 electrons, with two neutrons, which identify it as helium-4. And it certainly also has 2 electrons going around it at certain, so we say for the moment, orbitals. Now, helium also comes very commonly in the 3 form, where we have 2 protons, but 1 neutron has been taken away, so we have only 1 neutron, and this is now known as helium-3, or light helium. So these are pronounced helium-4 and helium-3, and we have 2 versions of hydrogen, basic hydrogen or heavy hydrogen, hydrogen-2. And we will use these as we determine what powers the sun. At the center of the sun, the temperature is very high. It's at 10 to the 7th degrees Kelvin. And when you heat up a gas, then you increase the motion of the particles in that gas. The particles in this room are moving at a certain speed, and if the temperature in this room goes up, then the speed of the particles goes up also. So at the very center of the sun, the temperature is so high, the particles are moving so fast, the density is so high that these particles bump into each other at very, very high speeds. So what they do is knock all of their electrons off, so all of the particles appear as bare nucleus, and the electrons are moving around separated from their original parent atoms. And that is a state of a fully ionized gas called a plasma, and that is what occurs at the center of the sun. Now, the dominant gas in the sun is hydrogen. It's almost all hydrogen. So we'll just concentrate our attention now on a lot of bare hydrogen nuclei. Now, a bare hydrogen nuclei just consists of 1 proton. So what we have is a lot of hydrogens going around in the sun. And you can think of them as protons, if you will. So we can just call them P. So we have a lot of protons going around. Many, many, many of them traveling at very, very high speeds. Now, these 2 protons, they both have the same electric charge, which is positive. So when they come near to each other, then they repel and they fly off at very high speeds. However, since the temperature of the sun is so hot, they are traveling so fast that before they can turn around and change direction and run away from each other, sometimes they approach to a distance of less than 10 to the minus 15 meters. And when they approach to a distance of less than the minus 10 to the 15th meters to each other, then the strong force is felt. These particles also attract each other via the strong force. Now, the strong force is 137 times stronger than the electric forces which is tending to separate them. But it is such a short range force that it only kicks in when they get very, very close to each other, 10 to the minus 15th meters. So in order for them to reach that degree of closeness before they turn around and fly apart, then the temperature has to be very, very high, which gives them a very great speed. And as they approach each other at high speeds, they slow down, then they turn around and go back because of their repulsion. But if they're going fast enough, then they get just close enough that the much stronger strong force kicks in and they are bonded together. Now this occurs to a very small percentage of the protons that are at the center of the sun because there is a distribution of speed. Some are very fast, some are medium speed, and some are slow. But the very, very fast ones, as they collide, they will stick together. Now, it has been known that what happens when two protons go ahead and stick together with each other, then what happens is a unit is formed of one proton and one neutron. Because what is kicked out is a plus charge, a plus positive electron is kicked out, and what is also kicked out is a neutrino. So the flying out positron and the flying out neutrino take energy away. Now because the positron flying out has a positive charge on it, it takes away the positive charge of one of the protons and it leaves it behind as a neutron. So now where did this energy of these very fast moving particles come from? It comes from the fact that these two particles, when they are bonded together, have less mass than they had when they were separated particles. The total mass of these two particles is less than the added mass of those two particles when they were separated. And because energy is equal to mc squared, if you have less mass here, then you have less energy between these two particles, and the energy difference is taken away. So this is where the energy that powers the sun comes from. It is in the form of these particles that escape when these nuclear reactions take place, and these escaping particles transmit that energy to the rest of the gas, and eventually it works its way to the surface and it comes off as sunshine. Now there's a complete cycle that takes place. The next thing that happens is that this now state is called hydrogen 2, or heavy hydrogen. Now this heavy hydrogen will find another heavy hydrogen, and these two will combine, and so there will be two protons, and one of the neutrons then also escapes, and there is only one neutron left, and so the escaping neutron also carries off energy, and this is known as helium-3. And once again, the particles in helium-3, their weight when the three of them are combined is less than the weight of the ingredients that came into them. So therefore more energy is also carried off. Now in another part of the sun, there could be also a PP reaction that produces a heavy hydrogen and another heavy hydrogen, and these could get together and they can produce another He3, helium-3. Now the two helium-3s will also combine, and what they will form is an actual helium-4, a normal helium atom, and the two extra protons will fly out to the side. So the net result is that you have 1, 2, 3, 4 protons going in, and then they pick up two more protons as they combine. At this point you have two protons coming in and making these into heavier helium-3s. The protons come in. Actually, this is just a single proton that comes in at this point, so let's correct that. So it's a single proton coming in here and a single proton coming in here. So these two protons come in, these two protons come in, but those same two protons come out just a moment later. Now the sum amount of the mass that's present in the helium-4 is less than the 1, 2, 3, 4 protons that went in to make this final product, and therefore the difference in the mass emerges as the energy of the particles that are spat out. The particles that are spat out in the form of gamma rays. There's a gamma ray that comes out at this situation, and the positron that's emitted earlier. And in each case, the particles that are finally produced have less mass than their ingredients, and therefore there's a difference in mass, and that mass is converted to energy, and that energy works its way up in a very, very long time to the surface of the sun and emerges as sunshine.